I'm
There's a
making it
first
clear.
time for everything, okay? There's a first time for everything. So it's fine. It's our
Yes,
first
yes.
time. Oh my
uh,
gosh. How is it over there in Germany today?
Cold and rainy as usual.
Oh my gosh. Cold. I feel like that country is never, ever, ever going to let up with its coldness and raininess,
Yeah, no.
especially with the scam that you'll get like 3 days of summer, and that is exactly that.
I
Like,
really think that's just the north. I think the south gets more days of summer.
really? Okay, yeah,
I've
well,
seen
maybe.
pictures. Yeah, probably.
Maybe I don't know, because like I feel like that's not even like a northern Germany thing. Like that is like a north thing, because I can remember when I was in Sweden, and like even in the Netherlands, people were like, I can remember there were like exactly 3 days in Stockholm that it was like, I think 28 to 29 degrees Celsius, and the rest of the time was like cold-ish and dreary, and like these Swedes are walking around with like short stuff, and I'm like, guys, um, hello, it's not summer. It's not summer.
Listen, anything above 20 degrees is summer. So
Hi, boy. No, no. I'm sorry. I'm sorry. I do not buy that. I'm like, you all need to come, move your country to the southern hemisphere, to where South Africa is, so that you'll know what summer looks like.
oh my gosh, they would die. That is too
They
hot.
would. They would. They would. Oh my gosh, no. That would be terrible. But yeah, so I was like, no. So I'm sorry. I feel like you've been scammed. You've been scammed.
It's fine. It's nice and autumny. Yeah, I'm gonna buy the special. I think we already bought the special autumn tea. I just now need to find a good chai and I'll be set.
I feel like you need to get like a good black tea and some good chai spice.
That is a lot of work, so I'm just gonna buy the
I
pre-mixed
mean,
one.
like it's a lot of work, but I feel like it's worth it.
I disagree. I'm just gonna go to the tea store and see and get their pre-mixed thing.
Okay, fine. Well, but
Listen,
in case what?
the tea store does good work. It's fine.
I guess if you want to leave it to the experts, then I guess that is fair also, because to be fair, making like proper nice chai is actually like, it's actually a lot of effort. But one has to do what one has to do. Now I want to know, did you get a notification on your side yet, or not, on
I,
Facebook?
I don't think so.
Really?
I will
Oh,
check on my I don't know, Facebook notifications I kind of ignore because they're annoying. Yeah. Wait, where would it show up on
I
the
I
timeline?
I actually, yes, it should probably.
Uh, yeah, I
Let me
might
just.
not see it then because I only have Messenger on my tablet and I don't seem to be getting notifications on my phone.
Right, 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 right. I see. Oh no, it's
Yeah.
fine. It's fine.
Okay.
Oh wow, like yeah, yeah, chatting about eigenvalue problems. You know what?
Okay.
Like at some point, I feel like I want to like play like a game. And yeah, if you are here in the comment section, hi everyone. If you are here in the comment section, please do say hello. We are kind of just hanging out today, Mpheng and I. Um, and yeah, we are just keeping it extremely chilled. We're gonna solve a math problem in a little bit. So really, really looking forward to that. But yeah, if you are here, please say hello in the comment section so that we can give you a shout out.
Mm.
Do you know, like, I really want to see like how it is. You know what? Whatever, it's fine. Oh, hi Michelle, how are you? I hope that you
Ah,
keep
okay.
warm there. Michelle's there close to the sea, I think. I hope that the sea
Yeah.
that the sea isn't too cold today. Yeah, well, let's jump in, right? What do you
Okay.
say? Let's jump in and let's solve this problem, because this problem is not going to solve
Yeah.
itself. Oh gosh. Okay, let us jump into this then. So I'm going to like restart the screen sharing, and can you see my
Okay.
screen?
Yeah. Well, I can see it.
Okay, brilliant, brilliant. Right, then let us just go then. Oh gosh, hey, I must say,
Yeah.
with these ODEs, ordinary differential equations, like I can remember, oh, yeah, oh Lord, yes, hey Michelle, wow, I can imagine that it must be freezing there where you are. Oh my gosh. It is nice to be on the other side of the screen. I can imagine.
Oh gosh.
Michelle always goes live regularly from her page as well with daily guidance and that. So now I think she's happy just to be watching a live video and being the one who's like doing it. No,
Okay,
so
that's a little scary, but anyway.
well, I mean, yeah, you know, and then like afterwards you like kind of forget about like what's happening.
Oh boy.
So
Feeling a
anyway,
lot more apprehensive now, but okay.
are you feeling a lot more apprehensive now?
Yeah, it's fine. Let's just get on with the problem
Okay,
then.
fine, let's get on with it. You know, when
Okay.
I was in first year, right? And like I saw these things like ODEs, and I'm like, why are these people talking about ode? Ode to what? And then I realized
Oh,
that it read
the
ordinary differential equation. Ordinary, of course, because the derivatives are total derivatives. And of course, here we have that y itself is just a function of x. So one variable, so that when we take its derivative, d over dx, with respect, where we look at its change with respect to the independent variable, the single independent variable, then we call this derivative ordinary. Ordinary. So it's not
ordinary.
that special, except for when it's partial. Then it's a bit more
Yeah, that's
special.
it. I'm trying
So,
to remember which ODEs did we do in first year?
oh gosh, in first year, I can remember we did Newton's law of cooling. So that
Oh yeah.
is kind of like, and then we also did this this ODE, dB over dt equals b, where the solution is obviously just like this growing exponential function, like that.
Yeah.
I
Okay,
can
yeah.
remember we did that, and then I think we did a couple of second order ODEs as well. In fact, it's this one's cousin. I think it was like ay prime prime plus by prime plus cy equals to d. Actually, let me take out the d for now, and then just put it equals to 0. And then we just say that that is the homogeneous ODE. But these all had the initial conditions, of course, and they obviously just said that at a particular value x0, the function must be the value y0. And because this is second order, so it needs two of them to completely determine all of the constants, we then also say y prime at x0 is equal to, let's call this y1. So we had that, and then we solved that. But we didn't do, and of course, this we called an IVP, or an initial value problem. Yes, thank you. Thanks, Michelle. Yes, definitely. I mean, that is our hope, that we, you know, Mpheng and I are just hanging out here and be like solving a couple of math problems. I mean, really, like we said, people honestly don't need to know anything about maths. If you want to just come hang out, you are more than welcome to. You can come and listen and see what Mpheng and I do. And yeah. So yeah, so these were IVPs, right? The initial value problems. And the key with these initial value problems was that we specified the value of the function both at the exact same point in the domain of the function. The domain is the set of permissible values. So that is what we meant by initial value. But these are different from the classic boundary value problems, because with the boundary value problems, what we will do is that we will say, okay, fine, we are looking for a function that is going to solve this ordinary differential equation over here, given as it is, but we haven't spoken about what lambda is yet. And here we are saying that at the one end of the domain, the function should be one value, and at the other end of the domain, the function should be another value. So that's the difference between the initial value problems and the boundary value problems. Initial value problems ask us which function satisfies at one particular point in the domain. It is these values that we are prescribing, and at the other or with the case of the boundary value problems, we are asking, we are looking for a function that at the one end of the interval, which is the boundary, it is one value, and at the other end of the interval, it is another value, or whatever that value is that we are going to prescribe. So in this case, we are going to take a look at the, so Mpheng, so we didn't do the boundary value problems in first year, because that we cover in second year because they are slightly more difficult. Let's take a look at some comments. Oh, hey, Nathan, how are you? How are you doing? Are you well? Are you all right? Are you keeping warm there today? Is it cold where you are? Let us know in the comments. Oh, yes, hey? Righto. So yes, so here we are. So this ODE is actually, I like this ODE, I really do, because like for me, like as a boundary value problem as well, like it's like the most friendly of the lot, because some of them can just become, hey Nathan, how are you doing? You are warm with maths in your soul. Nathan is warm with maths in his soul. Mpheng, do
Yes,
you
maths
feel
warms
warm
us
with math?
all.
Sorry?
Yes, it warms us all.
It really does warm us all, and it also wakes us the hell up. Oh Lord, do you remember those 8 o'clock lectures in the morning? Oh wow.
Vaguely. They were rough. Anyway.
I can remember you always used to come in like with a Coke.
No, that was coffee.
Oh wait, the other girl you came with had the Coke.
Probably, yeah.
Yes.
I always had coffee.
Oh, coffee, Lord. Yeah, hey. 8 o'clock and 9 o'clock, those were like dedicated to maths. Wow.
Yeah.
Like that was an actual thing. Yeah, wait, we are chatting. So yeah, so I mean, I like this boundary value problem because for me, like for all of them, it's actually the most friendliest of the lot. So yeah, y is the unknown function that we want to solve for. And then this value, this thing over here, which we are going to call lambda, lambda. So that is, so I'm not going to call it by its technical, I'm not going to call it by its technical name yet. I'm just going to say that it's a value that we don't know what it is yet. So we're going to just call it a constant. So this thing might be a real number. So something like 2.5 or 3 or pi or whatever. It could be an integer. So like 1, 2, 3, 4, 5, -2, -7. Or it could be, I don't know, rational, it could be irrational, it could be something else. It could even be like a complex number. We don't know yet. So we are going to see, like, what pops out here when we solve this problem. Yeah, so we're going to do that. And so here, essentially, if I want to write this in a more illuminating form, I can write this as y prime prime equals to minus lambda y, where I'm making no assumptions on lambda at all. And over here, all I'm going to say is, I'm going to ask is, I never thought of differential equations this way. I don't know if you thought of them this way before, Mpheng, but like, like with this particular differential equation, when it is in this form over here, like I always told when I thought about these things, I always said, like you have to ask yourself, you are asking for a differential equation solves for a function, an unknown function. And here, essentially, you are asking for what is the function y of x such that if I differentiate it 2 times, is going to give me back the original function, but it's also going to be multiplied by some scalar constant negative lambda. Have you thought of ODEs that way before?
Yeah, that's kind of how they teach them in the waves and vibrations course. The physics waves and vibrations course, yeah.
Oh, yes, hey, that's actually useful. But like, I don't remember. I feel like maybe some people might have like spoken about it like this when I was in lectures. I don't remember because wow, that was ages ago. Wait, let me see. Nathan says, I saw Patrick with a piece of graph paper yesterday. I think he must be plotting something.
Oh, wow.
Okay, thank you for the dry humor. Oh, Nathan says coffee for maths, Coke for organic chemistry, and these are the days of our lives. Thank you, Nathan.
Oh
Thank you. We will most
God.
definitely keep it up and continue doing the videos. But coffee for maths, actually, coffee, I feel like in general for science, though.
Yeah.
Coffee for science.
I guess it depends on the time of the day. Coke might also work, actually.
Yeah, or Pepsi. What's your preference, Coke or
Yeah.
Pepsi?
Do they even have Pepsi on campus? I don't think I ever saw
I
it.
feel like they might have, like at least one place on campus might have had Pepsi.
I've never seen it. I don't know. I don't remember seeing it. I think it was like a Coke area, strictly. Because then they would need different, don't they need like different fridges? They can't put the Coke stuff and the Pepsi stuff in the same fridge or something like that.
Listen, the Coke and the Jive were in the same fridge. The Coke and the Jive were in the same fridge.
I don't think that's legal.
Like this is between like, is it legal or do we care? Because
That
they
is
are
true,
all
that is
soft
true.
drinks. I mean, if it was up to me, I'd probably put like the Coke, the Jive, the ginger beer, and even like the 7-Up and the Double O all in the same things
Oh
together.
gosh.
It's only the
I
bash
don't.
that I'd keep separate.
Well, you better hope that Coke doesn't catch you doing that then.
They can come for me if they want to come for me. It's fine. To quote a person we both know, if you're gonna come for me, come hard. Oh my gosh. So yeah. So anyway, so I think this is. I mean, like, you know, I think for me this is a really cool way to look at to look at a differential equation, because you know, like you're so used to solving like linear or algebraic equations where you just go like 2x plus 5 equals to 3, and then we can solve, and then you get a number, and it's like you solve a differential equation and you're like, wait, what? I'm getting a function out of this? Okay, that's weird. And like, if that's hard to come to grips with, like you solve these things on the computer. Oh my word! Do you remember back in applied maths when we solved these things on was it Octave or MATLAB that we
I
solved
think
it
it
on?
was MATLAB.
Oh my
I think it
god!
was MATLAB.
Oh my gosh! Like, do you remember? Do you remember that they how weird it was, like when we used Euler's method first, and then we get like this like array of numbers out, and you're like,
Yeah.
wait, what?
That was not fun.
Like I can remember, like I had to sit there in front of my computer and I had to go like, wait, what? Wait, what? Why is it not giving me the function? Oh, it's evaluated at like a set of points. Oh, that's why. Oh,
Yeah,
okay.
that's like,
Oh gosh.
yeah,
Uh,
extremely unhelpful, actually.
yeah, exactly. You're like, did they go there? Yes, they went there. Yes, Nathan, we did just go there. We did go there. Oh my gosh. Yeah. So anyway, so now, Mpheng, what do you think? Which function, if we differentiate it twice, is going to give us back the original function times some sort of constant, maybe?
Well, if I'm thinking in physics terms, it's probably going to be some combination of sines and cosines.
Definitely, but also the
Also with,
exponentials.
yes, exponential functions as well.
Yeah, the exponentials. Because I mean, yeah,
I can't remember.
yeah, you can't remember?
No, I was just thinking why those are excluded, but I'm just going to say once we work through it, I'll probably remember.
Right.
But there is a reason why the exponentials are excluded.
Well, yes. With this particular problem, with these boundary conditions, yes, we are going to find that some of these exponentials are excluded with these specific boundary conditions. Because for others they can be included. But so I mean, so yeah, I'm going to ignore like the minus sign in front of the lambda completely for now, and I'm just going to say as an ansatz. Ooh, let me write this properly. Heibo. Ansatz. So as an ansatz, we are going to say let y of x equal to e to the power of rx, like that. So that if we differentiate this twice, So every time we differentiate, we're going to make use of the chain rule. So the derivative of e to the x is e to the x, thankfully, but with the chain rule, we need to also differentiate this argument here. So every time we differentiate, a factor of r is going to come out. So we're going to essentially have here that we have r squared e to the power of rx, like that. And then if we sub this into the ODE, we are going to get something like r squared e to the rx plus lambda e to the rx equals to naught. And then because e to the rx is absolutely never zero, thank heavens, exponentials are like this, love them. We can just divide through everything, and then we get something that r squared is equal to negative lambda like that. Woo! So that is where we are at. So do you remember?
Wait, hang on. For the one question, for the ansatz solution, does it matter if you have a constant in front of the exponential?
No. Thank you for asking. No, it absolutely doesn't matter, because I know some people do put in like the constant over there for generality. But it doesn't matter, because I mean, if we put it in, we are anyway just going to get the constant in the ODE, and then it itself is going to divide out.
Okay.
Yeah, so it doesn't matter. I mean, yeah, we can put it. Sometimes I don't feel like putting it, then I don't put it. Usually I will not put the constant if I know that the constant is going to end up being like 1 or 0 or something like that. I'm just like, shh, guys. The constant must sort itself out.
Okay, let me substitute this in.
Oh.
No, I'm just okay.
Yeah. No, what did you say?
No, I was just substituting in the stuff, but you can carry on.
Oh, right. Okay, cool. So I mean, even in this over here, we made a big assumption implicitly. And the implicit assumption that we made here that lambda was not equal to 0. Because remember, previously we didn't say that lambda could be in we didn't say what lambda's value was. We also just didn't say what lambda. I just said lambda is a constant. But lambda could possibly be 0, or lambda could not be 0. We don't know what's going to happen. So where it goes, nobody knows, but we're going to see now what's going to happen. So then we will see. So of course, this equation that comes out of here, this is called the characteristic equation of the ordinary differential equation. And of course, r squared or negative lambda, these are the roots of the characteristic equation. So for us, ultimately, it is the roots of this characteristic equation that are actually going to determine exactly what is going to happen to the solution, because we will have to at some point resubstitute these roots into this ansatz over here that we made, depending on what r is, what we assume it to be. So we have to actually check all of these case by case, which is like a bit of a pain, but okay. And then depending on what r is, we're going to get something. So I'm going to go on here though, and I'm going to say, so this means that we're going to have r is going to be the plus minus root of negative lambda, like that. And then those are the two distinct roots of the characteristic equation. I mean, this is quadratic. Every quadratic equation has two roots, whether the two roots are distinct or not. So by distinct, we mean they are two different roots. So if you can remember from I always used to like these graphical interpretations. So here, of course, here it was the quadratic had two distinct real roots, because the parabola hit the x-axis twice. And then we also had this other weird case where the parabola only touches the x-axis once, and then that was two roots as well, but they are repeated. Like I remember people always get confused with this when they see the parabola touching the x-axis once, because they're like, oh, no, it's one root. And you're like, no, it's two roots actually. It's just that they happen to be the same root. And like, do you remember when you do linear algebra, that becomes a real pain because you have to like check like multiplicity, geometric multiplicity,
Yeah,
and algebra. What?
yeah.
Geometric multiplicity and algebraic multiplicity? What were they? Do you remember, Mpheng?
No, I don't remember that, but I remember that you had to make sure that the roots weren't repeated, or if they were repeated roots, you had to say. You couldn't
Yes,
just find
yes.
one and be like, that's the end of the equation. But yeah.
Yeah, no, because like as I remember when you had repeated roots, when you were looking for the eigenvalues, then it becomes a bit of a contention because then you need to ask like, are there enough eigenvectors or are there too few eigenvectors or what or what or
Yeah.
what or what? Oh gosh, Lord.
Oh, I
Yeah,
remember
hey.
that.
Those were tough times. But listen, you must actually keep those linear algebra things in mind because we are going to come back to them in like a few minutes time, or this is eventually when we get to this. So anyway,
Yeah.
so we have the roots of the characteristic equation then, which is just going to be plus or minus the square root of lambda. Oh, did I forget to include one last case here? I did.
Which case? Oh, with the
Yeah,
parabola doesn't touch.
yeah, where
Yeah.
the parabola doesn't touch the x-axis at all. And then oftentimes, like in school, when we are taught quadratic equations, we will say, there are no roots to the quadratic equation. And like they leave it at that at school level. And then you get to university and they're like, actually, let me just sip my coffee. Actually, there are roots to this quadratic equation. They are just imaginary, or in more general terms, complex roots. So obviously, since they are not real, they are not going to touch the x-axis at all. And you are like, okay.
How do I transfer to applied maths?
And then you transfer to applied maths and you're like, oh my gosh, the same thing just came back.
And then you're like, how do I transfer to physics? And they're like, nope, we got complex roots here too.
Yeah, and you're like, okay, engineering. Oh no, damn it, there's complex stuff there as well. And then you're like, okay, you know what? I'm just gonna give up. Like, I'm just gonna like, I'm probably just gonna transfer to law or something like that.
Like, no, it's fine, it's fine. We're working with complex numbers, whatever. It doesn't make sense, but let's just go ahead.
Oh gosh, yes. Oh wow. Yeah. So yes. So there is that case. There is that case too. So yeah. Let's see. So wait, let's go back to the comments here on the Facebook quickly and see. Righto. No. So we are still fine. We are still fine. So yeah. Where were we now with this problem? Yeah. Right. So what we're going to do now, so over here then from the roots of the characteristic equation, you can see that we actually have about 3 different cases here. Or well, let's say 2 different cases for now. So you can see that at least that the solution is going to be something for lambda not equal to 0. And then we also have to check the case where lambda is equal to 0.
Okay.
So
if we're starting with cases, is the first case the one where lambda equals 0?
Yeah, let's start there because that'll be likely the easiest. That'll be likely the easiest case to do, and then we can check the cases of lambda not being 0 separately because that you know is a whole other point of contention. Yeah, just hang on quickly. Let me just check something here quickly. You know, I feel like I should do. I feel like I should do a an Instagram story and be like, people come say hi on Facebook and solve math problems with us.
So it's a Monday morning.
So it's a Monday morning.
Can we not?
Listen. I had to do this. Oh my gosh, you know, I just took a sip of my coffee and I spilled coffee on my iPad. This poor iPad, you know how long I've had this iPad for since? I've had it since 2017. And this poor thing has been like, it has been through thick and thin. people have already upgraded to iPad 2 and iPad 3 and iPad Lite and iPad Pro, and I don't even know what what other iPads there are. And I'm like, to quote Elsa, this millionaire lifestyle, it's not for me.
Yeah, no, thank you.
It's like a whole actual lifestyle, but no, guys, no. Yeah, hey, yes. So yeah, so let's check the case of lambda. Let's check the case of lambda equals to 0 first, and then we'll go from there. So if we have lambda equals to 0, then we are going to have here then that the roots of the characteristic equation are going to be 0. And so this to us might seem like, oh my gosh, but does this mean that there's one root? No, there's two roots. They are both 0. Both of them are naught. So if we substitute this back into the ansatz, this means that we are going to have y of x equals to e to the power of 0 times by x. But they are, hey, Charles, how's it going? Thank you for dropping in.
Wait,
How are you doing? Are you keeping warm today on the Monday morning? Oh, wow, it's actually Monday afternoon now. So we are left with this, right? But the thing is that there's actually another solution that we need to get out of this. And I mean, I'm totally not going to go into this other solution that we're going to extract that also corresponds to the root r equals to 0. But I mean, you can get it from something like reduction of order, where you manually integrate the differential equation. But there is another solution that comes out of this. So I'm going to put in a constant C1, and then I'm going to put in the other constant C2, and this is going to be x e to the 0 times x, like that. So of course it is possible for the general problem to actually, yeah, it's possible for the general problem to actually show that e to the x and then x e to the e to the lambda 1 x x e to the lambda 1 x blah 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 blah, all of those x squared e to the lambda x, etc., etc. That whole set forms like the set of solutions in the case that you have this repeated root. So of course this is just the very familiar c1 plus c2x, and this is of course the straight line, just the regular straight line that we have over here. And I mean, if we do have lambda equals to 0, the differential equation itself just becomes y prime prime equals to 0. And there we are asking which function do we have such that if we differentiate it twice is going to give us 0. And the only possible function that we know of at the moment is going to be the function y of x equals to c1x plus c2x, which is the straight line. So to this then, we can apply the boundary conditions, because the boundary conditions we are now going to determine what this are going to determine what the constants are. So if we say, well, y of 0 equals to 0, this means that we have 0 being equal to c1. So the constant c1 at the very least is equal to 0. And then we have y at L equals to 0. So here we have then 0 is going to be equal to C2 times by L, like that. But, oh, great. I'm glad that you are warm and cozy, Charles. Charles says that they are learning all of the maths that they forgot from university. Yeah. This is the year we are just hanging out. We are solving random maths problems, and we are just relearning ourselves, and we are on our maths journey. I should probably hashtag that. Hashtag maths journey.
Oh boy.
Oh boy. I can already see the t-shirts and the fragrance line and everything coming in.
Oh boy.
Yeah, hey. Anyway, so there's this. So now, Mpheng, do you see that we have a problem here now? Because we now have the product of two things is equal to 0. But it's like L can't be 0 because we haven't, I mean, L is finite. I mean, L is finite. L is non-zero. It's not 0. So that means that we are now going to, the only other thing that we are forced into now is by saying, well, this means that C2 has to be equal to 0 itself because L can't be 0. So if we put all of these together, we then have that our function y of x equals to 0 is the only solution for lambda equals to 0. And this is, of course, relative to the boundary conditions. It is relative to these two boundary conditions that we have that we have imposed here. Of course, if we impose other boundary conditions, then of course we will get a different solution. But in this case, it is naught, straight up. Oh gosh. Don't you think that was a lot of work just to get 0?
Well, it's the easiest one still, so I'm not complaining yet.
Like, yeah, like actually, it is the easiest one still, hey? It
At
is the
least it
easiest.
wasn't that long, yeah.
Oh gosh, hang on. Let me just, sometimes one needs to, I'm going to actually share this. Oh gosh. Yes, hey? Are you still there, Mpheng?
Yes, I'm still here. Just
Right.
waiting for you to finish with your technological things.
I'm so sorry. You must understand, like I do this thing, like I work a bit and then I'm like, wait, I need to look at my phone first. And then I get back to the problem at hand. I guess through and through, I'm still a student at heart. Lord. Righto. Oh gosh, let me just get right. So there, right. So that is this, right? So let's move on to the case of lambda not being equal to 0 now. Oh gosh, this is going to be so good. Oh, why am I writing in red? It's actually right in black. Right. Lambda not equals to 0. Oh, yeah, the drama starts. Right. So lambda not equals to 0. So here then we are going to have that the roots of the characteristic equation are going to be r is equal to the plus minus square root of lambda. And that is going to be, that is probably going to be a bit of a point of contention now, because it means that we need to consider two particular cases. We are going to have to consider here, the case of lambda bigger than 0. And then we're also going to have to consider the additional case of lambda less than 0. Because, I mean, I'm sure that you'll agree, Mpheng, that these are going to produce two drastically different solutions.
Yes.
Yay, righto. So which case do you think we should deal with first? We're going to deal with positive lambda or negative lambda?
Let's go positive.
Right, yeah, because we should always stay positive.
Yes, that's definitely my reasoning.
I feel like I can turn like this whole thing into like a whole like motivational speech thing.
Oh gosh.
Oh gosh. You know, if I was like giving this, if I was like teaching this, I'd have probably like solved this problem in like, I guess like 10 minutes or 15 minutes, like at the most. Oh gosh, it's a nice just a chat. Anyway, right. So then let's go for positive lambda first. Mpheng, are you sure that we must go positive lambda first? Because I feel like
I've already said it. Let's just do it.
Okay, fine.
You can't avoid it forever.
I know we can't. You know what I would like to do? Remember those plants on campus that had like the big red fruits on them, and then you told me the one day, Patrick, please don't eat the plants on campus.
I probably did do that. Yes,
you did. You
campus plants.
No, don't you like?
I was right.
No. Like those plants had fruits that are actually edible. Carissa macrocarpa. I think they were called I called them Natal plums. They had like these. They were like these big red fruits like this, and the bushes were kind of thorny. Don't you remember those?
I still think you shouldn't eat campus plants. I don't remember them, but I stand by don't eat campus plants.
Well, I mean, yes, your reasoning makes sense because like they probably spray those plants, which means that the fruits won't be good to eat. But I mean, in general, one can eat those anyway. Oh, by the way, people, This live stream is being brought to you courtesy of Lactua virosa, the spiny wild lettuce, or is it prickly lettuce, whatever. Anyway, Lactua virosa. That is what this live stream is being sponsored by today. I think the next live stream is going to be sponsored by Shangela. I'm not sure yet. I have to check with her, because when I asked her this morning, she just looked at me and she was like, listen, I need to eat first. I need to think about it. Okay, cool. Well, then let's jump into the case of positive lambda first. All right, so positive lambda. So positive lambda, so at this point, like, you know, if you were only used to seeing the solving quadratic equations with real roots, then you are probably going to be a little bit like freaked out at the whole thing of positive lambda, because then you realize that this whole thing, so I'm going to call the one root R1, and then this is going to be the root negative lambda. And then the other root I'm going to call R2, and I'm going to call this negative, negative square root of negative root lambda. And the Shangela for Pope. Do you know what? I wish that scandal was actually still happening, because, you know, it would have been so lit. Shangela versus Olivia Pope. I wonder who would win in shadiness. Do you remember? Now? Did you ever watch How to Get Away with Murder? Yes, you did.
Yeah, I did.
Do you remember when they had the crossover between that and Scandal?
By then I'd stopped watching because it was getting a bit ridiculous. But
I totally enjoyed it. But they were going like, and then the only one person who can solve this is Olivia Pope. And I was like, what?
Are we sure about that? Couldn't call anyone else.
Like they had this whole thing with like built up to what's the highest court in the United States? Is it
the Supreme Court?
The Supreme Court, yes. And they're like built up to the Supreme Court, and Olivia took Annalise Keating there, and then it was like this thing, and then it was like, okay, cool, and now what?
Okay, so yeah, I made the right decision. Is what I'm hearing.
Listen, I'm going to rewatch How to Get Away with Murder at some point, because I feel like I kind of need like those like season 1 vibes in me for a little while. Anyway, so yeah, now we have something that is now negative under the square root sign. But of course, as you all might know, as you might remember, we can't have a thing that's under a negative number under the square root sign, because, you know, for us it's like, how do we say that if you take a number, whatever that number is, and you square it, you're going to get a negative number? And that is true if you're talking about the real numbers, but it's not true if you're going to talk about imaginary and complex numbers, because imaginary and complex numbers roll that way. They are fine with that. So over here, what we can do with the rules of surds is that we can just rewrite this as the square root of -1 times by the square root of lambda. And we can do the similar thing for R2, where we have negative times the negative square root of, the negative square root of -1 times by the square root of lambda, like that. And then now we can say, well, is it possible for us to have a number such that if we squared it, we get -1? Yes, it is possible. This number we are going to call J, where J we define as the square root of -1, so that if we square this number J, we are going to get -1. And this is, of course, yes, Charles, exactly. We are going to make use of complex numbers, yes. So yes, so Charles has it there in the comment section, yes. They gave us the correct things. Thanks, Charles. Yes, we're going to use complex numbers. But so Charles, I see, so Charles using the notation I for the imaginary unit. And by the way, this number over here is called the imaginary unit, because, you know, it's in our imagination. That's where it exists. No worries, Charles. That's totally fine. So Charles has used, Charles has spoken about I So Charles has used I as the imaginary unit, and that is also very common. What one will see is actually I being used as the imaginary unit. Mpheng, you are used to using I as well for the imaginary unit, right?
Yeah, usually use I. Yeah.
Right. So I'm sorry, I use J.
Okay. Bit weird, but whatever.
No, because the engineers themselves usually make use of J, but I'm not an engineer. I'm an applied mathematician, but I still use J because when back when I did my research days, back when I did those days, I used to work with I used to use I for something else. Because I used to do research in magnetic fields. So I would use I for something like an electrical current. I think can't remember anyway. So that for me meant that the only other thing that I was going to use is going to be J, which is the other standard. You will actually also see some people use K for the imaginary unit, but I mean I feel like we're not going to go there because that is just reaching.
No.
Although I've also in one very ancient textbook actually seen somebody use W for the imaginary unit, and I was like, ma'am, can you not please? Can you just not? Not that it was a ma'am who wrote the book, but yeah. Can you just not please? Let us stick to I, let us stick to J, and in some cases, if we need to, let us stick to K. But I, J, and
Yes.
K. But I, J, K. Okay, that's it.
Okay.
Yes, Charles says that it's fascinating maths putting 2D quadratics into higher spaces. It really is like, wow, like have you, Mpheng, do you follow the channel 3 Blue 1 Brown on YouTube?
No.
You should check out some of their videos sometimes. Like really, really interesting stuff they do. I think there's also Veritasium, if I'm saying it correctly. Oh my gosh, like I feel like at some point I keep away from these videos because like if I watch them it can be like 3 hours later and I've like learned so much and it's like, yeah, guys, I need to do my work as well though. Anyway, let's get back to it. So that means that we can write the roots r1 as j times by root lambda, and we can write the root r2 as a negative j times by root lambda like that. So that means that if we're now going to put into the ansatz, then the ansatz is now going to tell us that the solution is going to be C1 times e to the power of j root lambda plus C2 e to the power of negative j root lambda like that. And so now 3 Blue 1 Brown is amazing, Charles. 3 Blue 1 Brown is really amazing. I support you wholeheartedly on that. So of course now you're like, okay, fine. So like here's the first family of exponentials, right?
Ooh,
right?
Wait, you forgot the x's.
Ooh, highball. Thank you very much. Otherwise, I just have constants in the solution.
Yeah.
And that's not gonna work. Oh gosh, yes. So now we have like these exponentials. And the weird thing is like, for some of you, like, for some of our viewers who are perhaps not familiar with these things. So these are called complex exponentials. And it's not because it's complex. I mean, they are complex, but they are also not complex in not the mathematical sense. So these complex exponentials are actually very nice because they are actually, if you write them out, one of the ways that you can write them out is actually as a sum of sines and cosines, because this is how the complex numbers themselves are actually linked to the sines and the cosines. So we can actually write this as the cos of root lambda plus j times the sine of root lambda like that. And then similarly for the other counterpart, we can write this as cos of negative root lambda plus j times by the sine of negative root lambda like that. But of course, cos is what we call an even function. So for an even function, if you have some function f of x is that is even, then f of x and f of minus x are going to be exactly the same thing. Whereas if you have some function that we call odd, so for even functions, what they possess, oh bless you, what they possess is this very, very nice symmetry across the y-axis or the line x equals to 0. And then if you have another function, Mpheng, what was the rule for odd functions? Can you remind me?
F of x equals minus f of x.
Oh, no, f of negative x, you mean?
F of x equals, no, wait, what? Yes.
Of negative
no,
x equals negative f of x.
Hang on, let me just draw a sine function quick.
Okay. I think it's this.
Because sine starts at 0, right? And then
Yes. Sine starts at 0,
yeah,
so
no.
it does that.
Yeah, it is f of x equals minus f of x. No, f of minus x. I don't know. Minus
F of minus x is equal to negative f of x, as with the graph here. So so if this is
x, that's
a,
1.
then this is going to be f of a. Then this is going to be a negative f of a, and this is going to be negative a.
Yeah.
Yeah, so f of negative a is negative f of a. That's the odd function, and it produces this weird, kind of flipped symmetry across the line y equals to x. So cos is an even function, which means that we can still write then this as cos of root lambda, and sine is an odd function. So then sine of negative root lambda is just negative sine of root lambda.
One thing again, did you forget the x?
No. I'm just looking at the exponential.
You're not including it.
Yeah, no.
Okay.
I'm just looking at the exponential for now. But I mean, we can include the x like that. I think it's, thank you, Mpheng. It's actually better if we include the x so that it doesn't become confusing in what we're about to do next. Charles says that they learned complex transforms from that channel. Your complex transforms, Charles, can you just tell us what was that? Was that those Fourier transforms or what? Your Fourier transforms. I can remember I did a whole module on Fourier on Fourier methods. Oh, Fourier methods are absolutely. Did you ever do Fourier methods, Mpheng?
Yeah, for the waves and vibrations class.
Oh, so you all did a whole section on Fourier methods.
Yeah, the last, I think it was one of the last sections, but there's a whole Fourier methods section for waves and vibrations.
Oh my word, I love Fourier methods, honestly. Fourier methods, 15 out of 10, definitely do recommend, especially when you're solving partial differential equations. Yeah, and they turns the whole thing into an ODE. Most beautiful thing ever that I have seen, that I've sawed ever in my life. So using these rules for the complex exponentials, we can now actually rewrite after some work our solution as and I'm going to now put a tilde on top of the C1 to indicate that it's actually a different constant. But it involves these constants C1 and C2 that we've already worked with. Wait, C1 and C2. Why am I using? I must use C3 and C4 because we are now working with other constants. Yes. Hi, bo. There we go. C3 and C4. Okay. So this is C3 tilde, and this is going to be cos of root lambda x. Maybe I should just put the brackets to be absolutely clear, and then plus another constant C4 tilde times by the sine of root lambda x, like that. Yeah, so that is going to be the solution for the case of positive lambda, which means that the roots here were what we call purely imaginary. So it should actually point this out here. And there is a difference, some of you might wonder, what is the difference between purely imaginary roots and complex roots. So in general, any complex number we write as a plus jb, where a and b are real numbers, and they are not necessarily 0. So this we call complex. But now the thing is that when a is equal to 0 and you're just left with jb, This we say is purely imaginary. That is purely imaginary, because there is no there is no sort of what we call a real part to it. So what happens is that we can actually take these complex numbers and we can actually plot them on a plane, where over here we have the real numbers, and on the what we call the y-axis we have the imaginary numbers. And this is called the Argand diagram. Is it Argand? Argand? What is it?
I have no idea. I don't know what things are called.
Has it been that long ago?
I don't think they ever told us. Like it
Woo!
never came up. Why
Really?
did
No,
they tell us?
it definitely
No,
came
I've seen
up.
I've seen the diagram, but they never told us what it was called.
I can remember one of the professors told us, he said it was the Argand diagram. But anyway, so complex numbers in the Argand diagram exist anywhere in these quadrants over here, whereas the real numbers exist solely on this line over here, and then numbers that are purely imaginary exist solely on this imaginary axis over here. So that is this very nice sort of like 2D way of viewing complex numbers. And it also like extends, our notion of what are numbers. So in this way, we can actually say that the real numbers are in fact complex numbers as well, but they just have this part B equal to 0. So they are just, they just have A. And we call A the real part and we call B the imaginary part. So if the real part of a complex number is 0, the number is purely imaginary and exists on the imaginary axis. If the imaginary part of a complex number is 0, then the number is a real number. But if both of them are not 0, then of course they exist elsewhere in these quadrants, and then they are called complex numbers. Yes. So we have this solution in terms of sines and cosines, which is absolutely brilliant. So yeah, so we can now definitely impose the boundary conditions. Not me writing Imo's BCs. Imo's, we can impose the boundary conditions.
We can. That kind of looks like a P.
I mean, I had to squash the P in there. It's a small P. I just had to like squash it in, be like, oh, yeah. Oh my goodness. Oh my goodness. Sorry, wait. I need to take a quick social media break because people. Oh
Okay.
gosh. A general sense of felicity and hopefulness permeates the day, lightening the emotions and worries of the mind. As a result, people may wish to express their mirth in diverse ways, some by venturing out and breaking new ground. Ooh, that's actually cool. I'm actually going to share this. I'm going to share this. My friend writes like daily horoscope posts. So, and he actually does really great work. I'm going to share this on Facebook. Yes, I'm going to. Right. Let's impose the boundary. Let's impose the boundary. Yeah.
Wait, I'm still trying to like substitute back the things
What
to
things?
see what exactly the exponentials when we substitute them back into the original answer of the equation.
Yes.
Because
So
that changes the.
Yes. So what's going to happen here is that you're going to end up getting something like this. I can actually show you. You're going to get, if I can remember properly, you're going to get something like C3 plus C4 into cos of root lambda x. And then I think this is going to be something like plus j into C3 minus C4 times by sine of root lambda x, like that. You're going to get something like that. And then we make the identification that C3 plus C4 is C3 tilde, and this whole thing, J C3 minus C4 is C4 tilde, like that.
Yeah, okay.
Yeah.
That is
So
what I'm getting as well.
Yes, yes, yes. So it's just, and I mean, but it's okay because C3 and C4 are arbitrary constants, and so you know it doesn't matter. Their sum is an arbitrary constant, their difference is an arbitrary constant, and even if they do happen to multiply the imaginary unit, it's also chilled because that itself is some arbitrary constant, which we know is complex or rather imaginary. But you know, like. I can remember I said to my students when I first taught this way back in the day, and then they were looking at me and they were like, huh? And then I was like, yeah. And also like, we are going to just like kind of like forget about the fact that one of the constants is actually complex. And
Yeah.
just impose our own things on it. And they were like, huh? And I was like, just go with it, please. It works. The actual explanation is going to blow your mind, and like you're already looking like you'll need a minute. So
Okay, so I guess it doesn't matter that C tilde 4 is complex. C4 tilde? Is it C tilde 4 or C4 tilde?
C4 tilde.
Okay.
C for tilde.
Ah.
I am hot with the catchphrases today. It's absolutely amazing. I am absolutely hot with the catchphrases. Good work, Patrick. Good work. While Mpheng sits there and Mpheng is just like, what am I going to do?
Listen, let me finish my substitutions. I do not have time for dad jokes. Okay, I'm caught up now.
Road.
So I'm working with complex numbers. I do not have time for this. So boundary conditions.
Oh my gosh. Oh my gosh. Oh my gosh. Yeah, hey. Oh gosh. Wait, let me just see something here quickly. You know, I actually took a note of the timestamp of when we went live.
Yeah.
But let me just see. Oh no. Oh no. Okay, so it's this one, Fremont, California, United States. Oh, child. I must actually, there we go. Fremont, California, United States. Now I just have to, no, I made a note of the, time that we went live. But the thing that I used is using a location in the United States of America, and the time that we went live there was like past 3 in the morning, and I'm like, it is not past 3 in the morning in Cape Town. It is not.
That is weird.
Anyway, let us go on. So let's impose these boundary conditions. Oh, I love these boundary conditions. I love saying impose the boundary conditions because, you know, for me, like initial conditions are super chilled. Like they're like that aunt who is going to tell you, yes, yes, yes,
yeah.
yes. And then you have boundary conditions, and boundary conditions are just like, my way or the highway. It doesn't matter. We are going to be doing this thing now. I'm looking for this function that's specified, that satisfies these conditions, and I'm going to get rid of everything else that doesn't. So, phew. Boundary conditions have been on that self-improvement journey.
They make things a lot easier, that's true.
They really do, and they love the sound of their feet as they walk away from opportunities that were not meant for them. And there's silence.
I'm trying to remember. Okay, so we're substituting back into the solution that we have.
Yes, into these sines and cosines. What do you get? Let's see.
Okay,
so I have y of 0 equals to 0, and this means that I have 0 equals to C3 tilde times by the cos of root lambda. Ooh, why did I want to write root naught? Root lambda times 0 plus C4 tilde times by the sine of root lambda times by naught. So the sine of 0 is 0, right? Yes. So that's totally going to go away. And the cos of 0 is 1. So essentially, I'm going to be left with C3 tilde being 0.
Yes.
Alia.
Forgot the tilde.
And then y at L equals to 0. I'm going to have 0 equals to, so now I'm going to ignore the C3 completely because or the cosine, because I know that its coefficient is going to be 0. So here I then have only that C4 tilde times by the sine of the square root of lambda L is equal to 0. And now we are already left with the exact same problem again as before, because the sine of root lambda L is not 0 unless L is 0 or whatever. Wait.
So, okay.
Yeah?
Oh, no. So for the last equation, we have either C4 tilde is 0, which gives the trivial solution.
Yes,
or,
yes.
And we know lambda is not 0 because we already did that case. And this is specifically a case where lambda is not equal to 0.
Yes.
So we've got, okay. So what does that give us for C4 tilde?
So we have C4 tilde is equal to 0, which we are going to avoid in this case, because otherwise, like you said, yes, we're going to get the trivial solution. Or it then has to mean that the sine of root lambda L must equal to 0. So, I mean, if we say C4 is 0, then we're going to get the trivial solution. And that is going to be like, why did we make this effort just for 0 again? Why are you doing this to us? So let's assume that the sine root lambda L is 0 in this case. So C4 is whatever value we want to make it. So this then is going to mean that the sine root lambda L is going to be equal to 0. So this is then going to mean, so sine is only going to be 0 at all of the integer multiples of pi. So for our viewers who are not familiar with radians, so for our viewers who know, we've always in school, we were taught that a sine of 180 degrees is 0, and then we use all of the integer multiples of 180 degrees. That sine is definitely 0 at. But so for our viewers, we don't use degrees anymore in calculus, we use radians. So this is equivalent to saying that because 180 degrees is pi radians. So here we have then that sine of pi is 0. So sine is going to be 0 at all of the integer multiples of pi. So this means that if it is true that the sine is 0, then it means that we are going to have that root lambda L must be equal to some integer multiple of pi. And here we are going to insist that n is a positive integer. So why are we excluding n equals to 0? We are excluding n equals to 0 because it's going to give us that lambda is 0. And we've already checked that case. So we are disregarding n equals to 0. We are also not doing n negative because there's a square root lambda in here and, you know, etc., 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 etc. So here we are then left with the fact that root lambda is equal to n pi over L. Ergo, that lambda is equal to n squared pi squared for L squared, like that. And this is n being an element of the positive integers. So that means that these values of lambda are going to be something like pi squared over L squared when n is equal to 1. It's going to be 4 pi squared over L squared when n equals 2, etc., 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 etc. Righto, we have that, right? We are...
Yes.
Okay, brilliant, brilliant, brilliant. You know what? I'm hungry now.
Well, we've got one more case to go. Hang in there.
I know. I want from those Korean instant noodles, man. You know, last night I had the jajang flavor, the Korean black bean flavor. Oh, that was honestly so nice. I think today I want to make a okay. I think today I want to make the so they also made like the creamy carbonara flavor. I think I'm gonna make that actually. So yeah, anyway, right. So then this means that our solution here in this case is going to be y of x equals to C3. Oh, well, no, C3 is 0 we found. So this is just going to be C4 times by the sine of root lambda x, but root lambda is n pi over L. So we are just going to have this as n pi x all over L. And here we also have to note the fact that lambda is equal to n squared pi squared all over L squared. So usually, most usually, we would actually just write this as sine of root lambda x, root lambda n actually. So we're going to put in the subscript n to indicate that there's a different sign solution depending on the value of n. And then say, well, lambda n is actually given by this formula over here, n squared pi squared over L squared. So in actual fact, we should also put the subscript n by the y to indicate that it is a different solution y that corresponds to a different value of lambda. But you know, we usually don't opt to write the if the expression for lambda is simple enough, we don't opt to write the root lambda in. We just write n pi x over L because you know, yeah. Anyway, so yeah. So then this is going to be the solution that we have, and this is for lambda being positive. Yeah, so we have that, right?
Yes.
One last case. Let's power through it.
One last case.
Yay!
What's this case
And
3?
this, yes, case 3. This is lambda being completely negative. So yeah, we have R1, R2. So let's actually write this like this. So we have R equals to negative square root of negative lambda. But here now we have that lambda is negative. And this is fine because then you're going to have a negative times by a negative number, which is going to mean that this entire thing under the square root sign is going to be positive.
Yes. So we got minus square root of lambda.
Yes, so then here we are then going to say that R1 is equal to negative root lambda. Oh, gosh, let's write it like this. Negative root lambda, and R2 is equal to negative square root of negative lambda. But since lambda is now negative, the thing under the square root sign is going to be positive. So what we have now here is that these roots are real and they are distinct. The roots are real and they are distinct. And moreover, one of them is going to be positive and the other one is going to be negative. So we will say, and they have opposite sign. Like that. Yay! So now we are now sitting with this thing now that has, that we are sitting with two roots, real and distinct, and they have opposite signs. So they're going to be, so these roots are actually nicely symmetric like this. So they look like this. They are those roots. So for this, we can then again say that our function y of x is then going to be equal to, so we've used C1, C2, 3, C3, 4, so we must use C5. So this is then C5 e to the negative root lambda x plus C6 e to the negative root of negative lambda x, like that. Now, it is totally okay for us to leave it in this form over here. Totally fine for us to do that. But I'm not going to do that because I'm going to through a very complicated and well, it's not actually complicated, but through a series of various simplifications and everything, I'm actually going to whittle this down a little bit. And then I'm going to change this into y of x. I'm going to say this is equivalent to y of x equals to C5 tilde times by cosh. That's right. You used to add out cosh. And this is actually called the hyperbolic cosine. So yes, so there are actually so there are actually things that are called hyperbolic. So hyperbolic sines and hyperbolic cosines, they form part of the so-called hyperbolic trigonometric functions. So this is cosh of a square root of negative lambda x plus C6 tilde times by the this hyperbolic sine of negative root lambda x like that. Now,
Okay, not to derail us, but could we have the definitions of the cos
oh
hyperbolic, the
yeah,
cosh and the sine hyperbolic?
oh yeah, most certainly, most certainly.
Okay.
Let us write those out. So this hyperbolic, so this cosh of x in general is defined as e to the power of x plus e to the power of minus x all over 2. So this is called the hyperbolic cosine. And then we have the hyperbolic sine, which is defined as e to the x minus e to the minus x all over 2. And this is the hyperbolic sine. Hyperbolic sine. And then, of course, we have the hyperbolic tangent as well, tan h, which is then simply the hyperbolic sine divided by the hyperbolic cosine. And here we don't have to say, make the specification that the hyperbolic cosine mustn't be 0, because the hyperbolic cosine, as it turns out, is actually never equal to 0, which is really wonderful. Oh, so this is the hyperbolic tangent.
Okay.
So basically, you can then take this solution with the exponentials, and then you can, like, you can whittle it around, and you will get to these definitions. You'll get yourself to them. So now our viewers, you'll have heard that I've said cosh for the hyperbolic cosine, but I've surreptitiously said hyperbolic sine and hyperbolic tangent. So I know some people, some first timers, because I remember I used to do this where I used to go like, okay, so it's sine.
Yes, sounds great.
Sine. Sine. And I always tell my students, please do not go sine because it's going to sound like you're dry heaving. And if you do it enough, you're going to throw up. And I don't have time for people throwing up in my classes. I'll be very cross if you do. So please, we are going to say cinch.
I don't know if that's better.
It is better because the alternative is shine. So now you tell me, do you want to say shine of x or do you want to say cinch of x? Which is
I
better?
would like to abstain. I would like to abstain from this vote.
Are you abstaining? But you have to say though. I mean, personally, for me, personal preference, I prefer saying cinch rather than shine because I don't know, you're giving a presentation, you to yes, and you know that this is now shine of 2, and you are like, what? What is next? So over here, we are going to say cinch. We say cinch. And then correspondingly, the hyperbolic tangent is even worse because people go tan. Tan. Now, if you really didn't think you were dry heaving, now you really are dry heaving. So please, save yourself the effort. Don't throw up. Just say tanch. Some people say fan, but I feel like that's not. Then just say tanch. Say tanch or say hyperbolic tangent. Like honestly,
I think I'm just gonna say hyperbolic tangent. I don't know if people know what a tang is.
But I'm
just gonna.
But I'm saying what the tang is.
Okay, you and I will know what the tang is, but everyone else might be confused.
Yes. No. I think it's safer just to say hyperbolic sine, hyperbolic cosine. But so for our viewers, it's actually, you see that these hyperbolic trigonometric functions are defined in terms of the exponential. And I think it's actually useful to detract for a bit to actually tell you that the hyperbolic trigonometric functions themselves, sorry, the regular trigonometric functions, or what we call the circular trigonometric functions, so cos of x, in terms of the complex exponential, we define them as e to the jx plus e to the minus jx all over 2. And then sine of x is actually defined as e to the jx minus e to the minus jx all over 2. And then tan of x, as we all know, is then simply just defined as sine of x over cos of x, like that. So you can see that it looks, if you put them all together like this, it actually looks like the circular. So these here, the blue ones, we call the circular trigonometric functions. So they are the circular trig functions. Circular because they're actually defined on a circle. Because if you can remember, when when one does them in school, then you have, I think, then you have like this nice picture over here with a circle, and then you have your right angle triangle, and then this is R, and this is X, and this is Y, and then we define, oh yes, and you have this angle theta, and then we define the sine, the cosine, and that way. But it's actually being defined on a circle. Whereas the hyperbolic trigonometric functions are actually defined on a hyperbola. So these ones are actually defined on something that I think the hyperbola that they use looks like that, and then they define they define them that way. So so you have these two actually main types of trigonometric functions. One makes sense in a circle, the other makes sense on a hyperbola. So these come in general from a broader thing called conic sections, because if you have two cones, so I'm drawing these cones like that. You now want ice cream, and if you cut,
gosh.
I know, right? So if you cut the cone straight across like that, the cross section that you're going to get is a circle. And I think with a hyperbola, what was it again? If you cut it down like, I think it's if you cut it like this, then the cross sections that you get look like that. So they are types of what we call conic sections from the general thing. So the parabolas, you also get parabolas as well. And the parabolas you get, I think it was if you cut skew like that or something like that, I think. Can't remember. I must go and review my conic sections. Was it not something that we learned in first year maths? We didn't do. The engineers learn about conic sections, but we generally don't. Did we do conic sections? No, we didn't, eh?
No, not really.
Yeah.
I think they came up a bit in the dynamics course, but that was about it.
Oh, did they? Wow. Yeah, I don't even remember what happened in dynamics. Yo. I don't even remember what happened. I remember the first semester of dynamics being all like, what's going on? And then the second semester of dynamics being all like, it was, yay, it was so nice because we did like that whole orbital problem, and that was the most amazing.
Yeah. The
honestly.
mission to Mars. That was
Yeah,
nice.
no. I think the one. No. You all did the mission to Mars.
Yeah, we did the mission to Mars.
We did the mission to, I think it was Eris. No. It was an asteroid called Eris, I think. I think it was an asteroid called Eris. So not the outer planet. Or was it 463? Whatever. Anyway, it was an asteroid in the asteroid belt. We had to work out the whole orbital plan and everything, and the time there, and the journey there and the journey back. It was that we had to work out.
Yeah, it's the same thing.
Yes, it's the same thing. It's the same thing. Just the
thing.
location is different.
Yeah.
Yeah. Anyway, so that was that. So basically, these are the two main types of trigonometric functions that we work with. There are what we call parabolic trigonometric functions, but they aren't used because they're considered to be very trivial. So like people don't really use it. You can define them, but like honestly, no one has time. Like the one parabolic trigonometric function, I think is like the number 1. And then the other one is like 1 plus x squared or something like that. And people are like, yeah, we've made up enough stuff for today, hey?
Yes.
And then of course the other ones which we don't really talk about, which we might actually speak about in very much later streams, are the elliptical trigonometric functions. Oh, I love this. I'm gonna write those down quickly. So they are so these 3 that I wrote down are called the elliptical trigonometric functions, and they are lovingly called sin, kn, and dn. Sin, kn, and dn.
Oh boy.
I'm sorry, I'm
Gets
making
better,
a fool of
actually.
these. I'm making a fool of these things' names. It's absolutely amazing. No, but anyway, so sin is called the elliptical sign. Kin is called the elliptical cosine, and then we don't say din, we say delta amplitude. So there isn't actually there isn't an elliptical tangent at all, but there is this weird thing called delta amplitude. And gonna leave it like that because there are different types of elliptical trig functions that we can define. Anyway, so I mean, point is here that our solution corresponding to the case where lambda is negative, so that is to say we had real things was what? Mpheng, what was it again? You can just tell us?
Real, distinct, and opposite sign.
Yeah, and then what was the solution that we wrote down previously? Sorry, I don't like scrolling. C5
tilde, cosh,
yeah,
root of minus lambda x.
Yeah.
Plus
C6 tilde.
Sine.
Cinch,
Cinch, allegedly.
Allegedly.
Apparently, allegedly cinch.
Allegedly, yes. Thank you. Yeah, the times the hyperbolic sign of the negative root lambda x. So now let's impose the boundary conditions.
Okay,
let's impose the boundary conditions. So y of 0 equals to 0 tells us that we are going to have 0 equals to C5 times essentially what is the cosh of 0 plus C6 tilde times essentially what is the sinh of 0. So if you now go into your calculator and so if you're using like an old Casio like me, you have to go to, I think it's where is it? Hi boy, I can't find it here. Oh dear. Oh dear. Did I really want to use the calculator? I mean, I don't need to because I know what these functions are.
Yeah, sort of.
Guys, I'm not going to use this. Where's, oh, here we go. Yeah. So you use the key that is marked HYP for hype. So you put hype, and then if you select, and so for me, so here you can see are the trigonometric functions. So if you select cosh, you'll find that the cosh of 0 is 1, and the sinh of 0 is 0. So this is going to go to 0 completely. And so we are left here, that's C5. So cosh of 0 is 1. So here we are left that C5 tilde is 0. Similarly, if we have y at L equals to 0, here we find that 0 is equal to C6 tilde times by the sinh now, because remember, we found that C5 tilde is naught, so we just completely just like leaving it alone. So sinh of the square root of negative lambda L is equal to 0 like that. And so now we have two options, that either C6 tilde is 0 or this sinh term, this hyperbolic sign is 0. So now the tricky thing with hyperbolic sign, so I'm actually going to draw it out for you. The hyperbolic sign actually looks like this, as I've drawn over here now. So this here is sinh of x. So as we can see, the hyperbolic sign is actually only 0 at the point 0. So that means that it's impossible for this hyperbolic sign to be 0. The hyperbolic sign of negative root lambda L, which means the only other conclusion that we can come to is that C6 tilde must be equal to 0. So this means again that with these boundary conditions, we are going to get the
Sorry,
trivial
that was my door.
solution. Oh, no worries. Do you need to go and get it?
Hang on.
Right. This is time for a message from our sponsor, Lactua virosa. Lactua virosa grows extremely, extremely tall. It usually has prickles on the undersides of its leaves, and it kind of looks like rocket. Lactua virosa, apparently, allegedly, please don't take my advice for it. Please don't take my word for it. Has been used for medicinal applications, but it's also a bit of a and apparently its milky sap that it exudes is also apparently good for like scratches and grazes and warts, particularly on the skin. But please do your own research. Do not take my word for it. I just see the wild lettuce growing in the garden, and then we pull it out because my father says, no, it's weeds. And I'm like, no, you can eat those. And he's like, no, we are not going to eat weeds. Anyway.
Just give it time, sir. Give it time.
Give
You will
it time,
be eating
yes.
meat in the future.
Honestly, we will be. This is why I feel like we need to start eating dandelions. I was actually going to check on the dandelions in the back. Right. So sorry?
No, I was just going to say the rules for edible dandelions are a little bit strict.
No, they aren't. All of the dandelions are edible.
Except the ones on the side of the road, though?
You're talking about that.
Like those restrictions.
Right. So all of the dandelions and its lookalikes are edible, apparently. And from a culinary point of view, they use exactly like you use the plant all in the same way. You can eat the entire plant from the roots to the leaves to the flowers. The leaves are apparently, I've had dandelion leaves before, they're very bitter, depending on where the plant grows. If the plant grows like out of cracks in the cement or on the side of the road, it's very bitter. Generally, we don't eat dandelions that have grown in the side of the road, because not only is the plant going to be very bitter, but you don't know what kind of toxins and that from the road runoff and that the dandelion is actually taken in. So definitely from the side of dandelions on the side of the road, like in the cracks in the concrete and that on the road, you're not going to eat those at all. Because they will contain things that are not good for you. But if they're like growing in your garden and you haven't sprayed your grass or anything for weeds or that, so they've just like grown in the wild, au natural, then you can eat those and you can eat the entire plant. It will be that you will find that the dandelions are like, you'll find that the leaves are very significantly bitter. But you can eat them raw, or you can saute them, or you can like make a salad out of them. It's really up to you. And then the root you can make coffee from. So I've got a couple of dandelions that are growing in our backyard now. But I want to like take them out for the root because I want coffee. And then depending on how I feel about it, I may or may not use the greens, because Shangela goes everywhere in the backyard. And
yeah, that's what I was gonna say.
Yeah, Shangela is very likely coming to. I can remember one day I was like checking on a dandelion, and Shangela came and she sat on it, like she went like poop onto the dandelion, and I was like, dog, why are you doing this to me? I wanted to eat that. Now I can't eat.
Not anymore.
You have sat on it. And she's all like, listen, I am the only dandelion in your life. No other dandelions except for me. Oh, Shangela. Right. So here we have trivial solution again. So it looks like then that we only have non-trivial solutions. For lambda being positive. And then in this case, so this is only, and then in this case, they are going to be one solution corresponding to each different value of n. And this is going to be, what was it, C4, right? C4 tilde sine times n pi x over L. And here we have that the values of lambda that each of these solutions correspond to are n squared, pi squared, all over L squared. So what we solved So what we solved, this problem y prime prime equals to minus lambda y with the boundary conditions y of 0 equals to 0 and y of L also equals to 0. This is a so-called eigenvalue problem. So I can always remember as a first year, like looking at first, I used to call eigenvalues eigenvalues. And then I used to call eigenvectors eigenvectors. Because, you know, this was back in first year when you also call an integral an integral. And
Who's you in this situation? Because
listen, oh yes, that was me. That was me. Except there was this other student in the course who did this when we got to the determinants of matrices, and I kid you not, she came in the one morning, she's like, oh yes, and the detriment of this matrix is that, and we are like, sis, detriment? Determinant. And she was like, no, it's detriment. And we're like,
listen, detriment is shorter, but also less correct.
yes, the detriment of, honestly though, like after some time, like when you're working so much with these determinants of matrices, you're like, actually, these are detriment.
Yeah, let's just get on with it. Determinants take so long to say.
Yeah. So this is called an eigenvalue problem. Why? So we say, and this actually comes from matrices. So if you do linear algebra, you often come to this problem AV equals to lambda times V, where lambda is some scalar. So a scalar, so this is to say it's just a regular number. And then this thing V is a vector. And a vector, we would, in the very simplistic way, know it as a quantity that has both magnitude and direction. But when we do linear algebra, we think of it in a slightly different way. So what A over here is what we call a square matrix. So this can be something like 1, 2, 3, 4, like this. So we write this as an array of numbers. And then this vector we can write as something like v1, v2 equals to lambda v1, v2. And in this problem, which we call an eigenvalue problem, or this is the eigenvalue equation, we are asking what value lambda is there such that if we take some vector v and we multiply the matrix by the vector, will we get back the original vector, but just multiplied by some other constant lambda? And so we are asking what value of lambda is there such that it is that? Because depending on the value of lambda, we will get a particular vector v that is going to, so that we have that if lambda is equal to whatever value, and we have the vector v that corresponds to that particular value of lambda, if we multiply this vector v with this matrix, we are going to get back the original vector, but just times by some scalar number, and the scalar number actually turns out to be lambda. And you know, so I never really realized, like I never really thought of like, why do you say eigenvalue? So in this case, of course, lambda is called the eigenvalue. And then v is called the eigenvector that corresponds to the eigenvalue. So it is always an eigenvector that corresponds to an eigenvalue. And I never knew why until I heard the Afrikaans name. And I don't know if you've heard the Afrikaans name, Mpheng, but it's called an eigenvector, an eigenvalue, sorry, in Afrikaans is called the eie waarde. And an eigenvalue, I mean, an eigenvector is called the eie vector. But the operative word here is the Afrikaans eie, which means own. So that it is a property of the matrix itself. The matrix has these eigenvalues and eigenvectors. You know, and we actually find these eigenvalues and eigenvectors from the matrix in a particular way. So they belong to the matrix, so they are a property of the matrix itself. So a here meaning own. And then of course you go to German and then you realize, oh wait, eigen, of course, own. Own,
Yeah.
own, own. So so what we will actually see here in this eigenvalue problem in the matrix sense is that we can possibly have that this vector v is equal to 0. Because if you have the vector v is equal to 0, then this product here on the left-hand side is going to be the 0 vector, and the product on the right-hand side is also going to be the 0 vector. And so this we say is a trivial solution. And we actually, and this is unfortunate because it means that regardless of what the value of lambda is, if v is equal to 0, then you're always going to have 0. You're always going to have, so the 0 vector in the sense is always an eigenvector for any matrix. But we don't want that. We don't want the 0 vector. We don't want v equals to 0. We want v equals to some non-zero thing. So to do this, then we say that we will, so to do this, then we will say that only we permit only non-zero values of v for as eigenvectors, but it could be that lambda could be 0. Lambda could be 0, may or may not be, but we are strictly only permitting non-zero values of v. Now, if you take a look at a v equals to lambda v, then I'm going to now write y prime prime equals to minus lambda y. And I can actually rewrite this in the form ly equals to minus lambda y, where L I'm going to define as something called minus d2 over dx squared. And this is called a differential operator.
Y minus?
It's just a convention. It's arbitrary.
Okay.
We don't have to. We can also say plus, but I'm just following convention as in like the way it's normally defined. So so matrices, if we do some linear algebra, we learn that matrices are actually what we call operators. So that if you take a look at this product AV, we can then see it as a matrix operating on the vector v and producing a particular result, and the result that it produces is lambda times v. In a similar way, if I take y prime prime equals to minus lambda y, and I define this thing L called the differential operator, then I can see that if I have this differential operator operating on some function y, the result that it is going to produce is obviously going to be y prime prime, the second derivative of y with respect to, sorry, I must actually take this out. Yeah, I must actually take this out. So if this differential operator operates on the function y, it is going to produce negative the second derivative of y, which then obviously if I carry everything over is where the minus comes from.
Oh, wait, the operator I think is missing a 2, d2 over dx squared.
Oh yeah, thank you, d2, yes. Yeah, that's right. Yeah. Thanks, Mpheng. Yeah, so in this way, I have now likened, the point is that this ly equals to lambda y looks exactly the same as av equals to lambda v. And then in this case, we can also say, well, if we can find some non-zero function y, so if we can find some function y of x that is not the constant function 0, i.e. the trivial solution, then we will say that the action of the operator on this function y, which produces negative y prime prime, is going to be equal to lambda, a constant, times by the function y that we get back itself. And in this case, if we can find such a function, and it is a non-zero function, then we will say that lambda is called the eigenvalue. And then we will say that y is called now not an eigenvector, but an eigenfunction. Eigenfunction. corresponding to the eigenvalue lambda. Like that. So in actual fact, this is exactly what we did in this problem. We found that the eigenvalues of this problem y prime prime equals to negative lambda y, we have found that the eigenvalues lambda are given by n squared pi squared over L squared. They are all positive, and the eigenfunctions that correspond to them are given by, and there's one particular eigenfunction for every eigenvalue, C4 sine times n pi x over L. And what we might generally see is that sometimes that these eigenfunctions are actually written without a constant in front of them, because the constant is actually arbitrary. It doesn't matter what the constant is. But we are going to, for the sake of generality, we are going to leave in the constant. But it is our understanding that the constant is the same for all of these eigenfunctions. But it doesn't really matter what the constant is anyway.
Yeah.
So
I think that depends on something like the initial conditions.
Yes, exactly. And so this, I should actually say over here, is dependent on the prescribed boundary conditions. So in this case, for our problem, for our eigenvalue problem, corresponding to, if we had that the boundary conditions were y of 0 equals to 0 and y of L equals to 0 as we had prescribed them over here, then we are going to find that the eigenvalues are given by this, and that the eigenfunctions corresponding to the eigenvalues are given by this. But if we change the boundary conditions up, we make them something different, like, I don't know, like if we say y prime at 0 equals to 0 and y prime at L equals to 0, then we are going to get completely different eigenvalues and completely different eigenfunctions corresponding to them. So in that way, if you mix and match the boundary conditions, they are going to change what the solution of the problem, what the eigenfunctions and eigenvalues are. So the eigenvalues and eigenfunctions. So in this case, this is why I said previously that that boundary conditions are actually a lot more imposing than initial conditions are, because boundary conditions have the power to eradicate whole classes of solutions just based on what they say, because the boundary conditions are saying, I am looking for a function that satisfies this value at this end, this value at this end, and everything else is going to be thrown away if it does not satisfy these conditions that I'm giving. And similarly, then you can say that the eigenfunctions that we get out of this regard the boundary conditions as sacrosanct completely, because regardless of what is going to happen on, the interior of the interval, at the endpoints, the eigenfunctions are going to say, I am going to go to these particular values that the boundary conditions have indicated that I must go to. So in this way, yeah, these boundary conditions are a lot more stronger than let's say the initial conditions, just because of this little quirk that we have. So yeah, so that is the eigenvalue problem. That is for the eigenvalue problem. Wow, it's been quite a bit, eh? We've chatted for quite a bit. What do you think, Mpheng? Any thoughts?
Yeah, I mean, I think we covered everything about the eigenvalue, like this specific problem. So like the specific type of problem. With the fixed boundaries and the, the second order, what's it called?
Yeah, second order differential equation.
Yeah.
Yeah, I mean, this is, like I said, when we teach students about boundary value problems and eigenvalue problems in particular, because we always tell the students, please, you need to be familiar with these core concepts from linear algebra. It's if you haven't learned any linear algebra and you And you now see the lecturer talking about, oh, this eigenvalue and this eigenfunction and then this and then that. You're going to be like,
Yeah,
what's going on here? And then you learn,
exactly.
and then you keep, but if you keep all of these linear algebra concepts in mind, you'll see that we are just extending them from what was first vectors and now vectors and matrices, and we are expanding them to functions. In so much as to say that we are saying that we are using this idea of a matrix in linear algebra that is seen to be as an operator, and the functions now we are seeing to be as special kinds of vectors. And it's completely okay. I mean, we're doing this by analogy, but it actually does extend this way. So yeah, I mean, so if you aren't familiar with those concepts, yeah, it's gonna be hard. It's gonna be very hard. It's gonna be very hard. But yeah, so this particular eigenvalue problem actually has a huge number of applications. Mpheng, I think we should cover at some point maybe one of these. I think a partial differential equation would be good to
Oh,
do, because this is where
yes,
this kind of thing does arise. And
yes,
then yeah, so but actually what's really fun is when we talk about solving this thing numerically. Oh, another numerical solution is another thing.
yay,
Yay,
so
but we're not going to do
fun.
that in this stream. We're not going to do that in this live stream. We'll probably do the numerical solution of this same problem in a different live stream, because yeah, solving boundary value problems on the computer, oh,
Ah,
that's a whole other thing. Like we get taught that in third year. The lecturer came, she gave us like a whole module on solving boundary value problems,
oh
and we were like,
boy.
yeah. But really,
Yeah,
really,
I
absolutely
need to
love it.
brush up on that first though, but yeah,
Oh yeah, no,
I
same here,
remember.
same here. All of those numerical methods. Yeah. Anyway, so yeah, so that's it. That's it from me at least. And Ping, how did you find this? Did you enjoy this?
Yes, yes. I mean, it was good to remember everything. Oh, there goes my door again.
Oh, okay. No,
Uh,
that's totally fine.
it's good to kind of be reminded of all the things that, like you're used to doing, and especially after second year. Wait, hang on.
Oh, nobody's.
Yeah, again.
Oh, I want
Uh,
dandelion now.
stay focused. Yeah, so I was saying that because once you're done with like second year, you don't
Mhm.
do this thing of going through every case,
Yeah,
because
no, you don't.
when you see the equation and you see the boundary conditions, you already know what
Yeah,
the solution is going to look like, and you know that the zero eigenvalues and the negative, wait, is it negative? The positive eigenvalues are already excluded.
yeah,
So there's a
yeah.
lot of like skipping over things that you do after second year
Yes,
that it's
yes,
nice to
yes.
go over again.
Yeah, definitely, definitely. I mean, there are also a lot of problems that we don't actually cover in the lectures. So, like, you kind of go from second year to third year, and then you cover more advanced stuff in third year. But then you realize that they are, because we can only teach like X amount of things in the allotted time.
Yeah.
So we have to pick out what is best for the students, because it's useless us teaching like this weirdly complicated problem, and then the students are like, what? So like we have to pick what is best first and what is most appropriate for that level, and then like kind of leave the students to in their own time find other problems. And like, I
Yeah.
mean, yeah, like I've been attracted to doing all of these other problems that we don't actually get a chance to do in lectures, because I'm like, these problems are so interesting. And like,
Yes.
it's like you get the knowledge and then you don't use it, and it's so sad. So it's like, no,
Exactly.
like, let's use this knowledge, people. Let's do these things. So yeah, anyway, so we're going to cover a couple of more things again in future soon. Yeah, so anyway, so any closing comments from Peng? What do you think?
No, I think this was pretty good and comprehensive. So
Cool. Great. So yes, so thank you for those of you tuned in. Thank you for watching. We really, really do appreciate it. We are going to obviously also post a replay of this onto onto YouTube, although of course the replay will also be available here on Facebook if you all want to come and watch. And thank you for watching. Thank you for tuning in and interacting in the comments. So in future, what we're going to do is, yeah, we're going to just proceed like this. It's really, honestly, it's very chill. There isn't, I mean, we'll try to work faster in future, but I mean, the point is just to hang out, solve a math problem, talk about dandelions and Shangela and K-pop or something like that in the end, or whatever, and then just just to hang out a bit, and then that's it. So nothing very complicated or anything like that. So anyway, people, thank you very much for tuning in. Really, really appreciate it, and we will see you all. We will see you all in the next live stream. Yes, cool. Thank you.